Hello guys, welcome to the channel. In this video, we'll be discussing Sandmeyer's reaction and the mechanism of the Sandmeyer's reaction. So what is Sandmeyer's reaction? In the previous video, we discussed about diazotization reaction, and you should be knowing that in order to understand Sandmeyer's reaction fully, you need to understand diazotization reaction. It's not a compulsory thing, but some of things which I might be saying in this video, for that you need to understand diazotization reaction. So in diazotization reaction, we took an aryl amine and then added NO2 to it in presence of hydrohalic acid. Here we take HCl and it gave us a diazonium ion. Fine, it gave us a diazonium ion and a full bond and a positive charge ion. And Cl negative, this Cl, it came here as Cl negative. Now this is Sandmeyer's reaction. Fine. This is diazotization reaction. Now following this diazotization reaction, we can carry out the synthesis of chloro-bromo or cyanido derivatives of benzene. What will be forming? We'll be forming these things, that is this molecule, and here we'll be joining to it either Cl, or we'll be joining to it Br, or we'll be joining to it Cn. Fine. Two Sandmeyer's reaction. So we'll be using either CuCl or CuBr or CuCl. Fine. Now we won't be able to generate through this reaction iodobenzene or chlorobenzene. The reason for that, you have to understand, is that this fluorobenzene, this cannot be used, this cannot be generated, because here for generation of this fluorobenzene, we will have to, here in the diazotization reaction, use HF in place of HCl. Fine. And this HF, it's an explosive, so it would be using, it cannot be formed. Fine. So why iodo cannot be formed? Because if you see iodine, it's very highly nucleophilic, so it won't be following this path. It's highly electrophilic, it's highly nucleophilic, so it won't be following this path, it will be following a different path. That's why we don't use this path for this molecule, because it has very high nucleophilicity, as a result of which a very high nucleophilicity, as a result of which it won't be following this path. And now let's see the reaction mechanism for this reaction. So first, what we take is that we take this diazonium salt of benzene or any aryl, aryl diazonium salt. We take that and we write positive over here and over here, and here Cl negative is present. Fine. So this reaction, it follows, let me write it down here, free radical mechanism. Free radical mechanism. Fine. Now free radical mechanism, if it follows that, then we will have to generate two free radicals, right? So in this step, we will be generating the first free radical. What happens is that CuCl is used as a catalyst. Fine, CuCl. So what happens is that this Cl forms a bond with this Cu. It gives us something like this: Cu bonded to Cl and bonded to Cl on this side as well. So this Cu, it was first in +1 oxidation state. Now it has converted to +2 oxidation state, and it is stable in +1 oxidation state. You should be knowing that. Fine. It's stable in +1 oxidation state. because in that it will be having a D10 configuration. If you understand that, so what happens is that this CuCl now will try to go back to that condition. So for that, it will be undergoing two steps. First, it will break this bond by homolytic cleavage, and we will get our first free radical. That is, we get this CuCl, this CuCl free radical. This is CuCl free radical. Fine. Also, along with this, we get our free radical of interest. That is this one, Cl free radical. Fine. Let's encircle this Cl free radical. It's our first free radical generated. To also take note of the CuCl action, here it has acted as reducing agent. Fine. Here it has acted as reducing agent. Why? Because it itself got oxidized. Its oxidation state got increased. If it is oxidized itself, then it has acted as reducing agent. Fine. So CuCl first acts as reducing agent. Now, what happens is that you can see this molecule. Let's see what happens in this molecule. So what happens is that this, take it here, fine, here, N triple bond N is present, fine. This is a positive charge over here. Now this N2 has to leave. And what happens is that this CuCl, it wants to go back to its original position, that is CuCl, fine. It has an extra electron, fine. It has this extra electron over here. So what it will do is that it will donate this electron to this nitrogen, fine. Also, this nitrogen now got one electron, and this will break this bond by homolytic fission. So what we would get is aryl free radical, our second free radical of interest. Let's encircle that, fine. Let's encircle this by pad as well. This is our second free radical of interest. Along with that, let's see what we have got. Along with that, we have got this N2, fine. N2, in this N2, you can see on this nitrogen, we have now 1, 2, let me mark with different color because it's not visible there. So it has now 1, 2, 3, 4, and 5 electrons, fine. So it has got back to its original position, so it will be released as N2, fine. So let's not go there about N2. It was only to take note of the electrons, record them, and along with this, we have got our CuCl, sorry. Along with that, we have got our CuCl back, fine. Now this CuCl, here you can see, has got back to its original position of +1 oxidation state. Now you can see this CuCl has itself reduced, so it acts as oxidizing agent, fine, reduced, fine. So this free radical and this free radical, they will now combine, and what we would get is something like this. This free radical, that is aryl free radical, plus this chlorine free radical, they combine to form chlorobenzene. I hope you understand the reaction mechanism. The same thing goes for bromobenzene and iodobenzene, right? Not iodobenzene, sorry, or cyanidobenzene, fine. So this is how it proceeds. I hope you have understood it. Let's take, see how long the video has gone. Okay, so let's take also BR, the reaction mechanism for BR. So for reaction mechanism of BR, we'll be taking isotization reaction first, in which we'll be taking aniline and we'll be acting on it by NaNO2 and HBr, fine, HBr. Now this will be giving us this molecule, that is what we call as diazonium salt. diazonium salt, all right, diazonium salt with Br negative, fine. Now here we will be taking CuBr instead of CuCl, fine. CuBr will be taken, so this will be coming to this, and it will be giving us our first free radical. And sorry, let's write the overall reaction here, and we will be discussing the mechanism. So we'll be getting this, fine. Yeah. So what would happen is that this Br, it would come to this. It would first, those CuBr will be acting as a reducing agent, and it will be converting into CuBr on this side and Br on this side, fine. Then this bond will be homolytically fissioning, and what we would get is Br free radical. Then this is our first free radical, fine. Also, this molecule, it will be giving us something like this, fine, aryl free radical along with N2, and also CuBr will be produced because now this CuBr over here, which had only one electron, that it would have been, that it would be given, that it would be giving to this N2. So this will be converted then to this CuBr will be converted then to this CuBr free radical will be converted then this to CuBr, right? Now, after this, we understand that after this, these two free radicals, they will be combining to form this molecule. So that's all about Sandmeyer's reaction, this molecule. Right? Yeah, fine. So that's all about Sandmeyer's reaction. We have three. Also, take note of this thing that EuCl, or that we can write Br, Br, or we can write CuCN. Fine. It acts as first. It acts as reducing agent, and then it acts as oxidizing agent, fine. So may take note of these two things because they are very important. It's the nature of Cu compound that we take in the reaction, fine. First it reduces, then it oxidizes, fine. I hope you understand it. Make sure to subscribe to the channel Chemistry Crux in order to get more videos like this. Thanks for watching.